I'm here still in Minitab, and I have currently the job. I'm working in purchasing for a health system. The anesthesiologists have read a study about a new brand of anesthesia that they are interested in and would like to try out. They would like to compare the variability in recovery time between the two brands, the current brand that we use and a new brand. And they've asked me to design an experiment by which they could determine not the mean recovery time, but how much variation there is in recovery time. They want to determine if there's really a difference in the standard deviation of the recovery time. Is there a difference in the standard deviation of recovery times using each brand? So that's what they would like to know. Okay, so first question I have to ask myself is, what confidence level should I work at? Should we work at 95% confidence? Or in other words, that's a significance of 0.05, same thing. Now, we are trying to do a hypothesis test. This is a two-variance hypothesis test. I'm comparing two standard deviations. So when we talk about two variances, we talk about a ratio. I'm going to be looking at a ratio of standard deviations. So rather than saying I want the standard deviation to differ by 1 minute, I'm going to look at it as a percent difference, as how much could it vary by, and then what's my power? What's the percent chance that I will detect a difference of that much or more? So let's start with, let's say I want to be able to detect a difference of 20% or more in the standard deviation. And what power level do I want? What is my chance of detecting it? So assuming that there really is a 20% difference, or more than a 20% difference, I want to have a high chance of detecting it. The most common power is 80%, but for this time, let's work at 90%. We will work at 90% power this time. Excellent. Excellent. Now the last thing to think about before I can just go ahead and do the power analysis in Minitab is that this one is a little bit different because it's a ratio. If I'm looking at a difference of 20% or more, what I'm really saying is that the standard deviation of one divided by the standard deviation of the other is equal to 1.2. Because 20% difference would be 120%. And so when you divide the two, you would get a 1.2 as your difference. So you're going to see I'm going to use that 1.2, and it came from this 20%. All right, so I'm going to go to stat. And this time I'm going down to power and sample size, because I'm doing a power analysis to figure out how large a sample. I guess I never actually said why we're doing this, did I? I'm sorry. If I'm designing an experiment, the key question is, how big does my samples have to be? How many people do I need on the new anesthesia? How many people do I need on the old anesthesia? My apologies. So let's go to two variances, because that's the kind of test we're doing. I'm doing it as a ratio of standard deviations. I don't know the sample sizes, but I do know the ratio is going to be 1.2, as we just talked about. My power value is 90%. Let me put that in as 0.9. I'm going to click Options, and I have choices. My alternative hypothesis, not equal. I just wanted to know, is there a difference? Are they equal or are they not equal? So that's great. My significance level is 0.05. And here I have two choices, Levine's test or the F-test. Our book does the F-test. And the F-test is good when your original data comes from a normally distributed population. But Levine's test works for any continuous distribution. It doesn't have to be normally distributed. We'll do the F-test because that's what our book does. But it wouldn't matter. It would just be a quick click to change it. And I'm going to say OK. I'm going to say OK. And you're going to see, whoosh, it made a pretty little curve for me, and it tells me right there my sample size is 319. But that's in each group. So in order for me to complete this experiment with the power that I wanted, I would need to have a sample of 319 people who get the new anesthesia and 319 people who get the original anesthesia.